Hi everyone, I am Aruna A, Assistant Professor, Department of Information Technology, SNS College of Technology. Today I am going to teach about the closure sets of functional dependencies in database management system. So before watching this video, please go through the functional dependencies as well as their axiom axioms. These are the things I have already uploaded in my channel. Please watch it. After that you can see this thing, so only you can able to easily understand how we can calculate the closure set based on the functional dependency. Closure of the set of functional dependencies. The definition for closure of functional dependencies is nothing but it can contain the complete set of all possible attributes that can be functionally derived from the given functional dependencies. So how we can identify the functional dependency, how we can functionally derive the thing is by using the Armstrong axioms or rules or the inference rule. So through that only we can able to identify, or we going to able to write down the complete set of all possible attributes. So in this axioms, we are having a 7 axioms. In my previous video, I explained each of the axioms separately. Please go through that video. And also in the description, I'm given the link of that particular video. So in this thing, the functional dependencies, it is denoted by the symbol F, and the closure of that particular functional dependency is denoted by the F plus. This plus denote the closure set of the given functional dependencies. So how we can identify the closure set of a single attribute or a set of attribute. So by using these three steps only, we can able to calculate the closure set of the functional dependencies. First, we're going to see what are the steps. After that, I'm going to solve the few problems for your understanding purpose. So step 1 is nothing but add the attribute which are present on the left hand side in the original functional dependencies. Similarly, we're going to write what are the attribute present in the left hand side, that we're going to write it in the closure set. That is the first step. In your second step, add the attributes present on the right hand side of the functional dependencies. So based on the step 1, what are the elements we are write it in the right hand side. So by using that right hand side value, we're going to identify is there any dependencies is available in our given functional dependency, that we're going to write it over there. In your third step, which with the help of the attribute present on the right hand side, check the other attribute. First attribute is completed. Next, we can check the second attribute, third attribute, fourth attribute, until all the functional dependencies is given. So this process can be repeated until the all possible attributes that can be derived and also that can be added to the closure set. Until this, we have to execute this particular process. Now let us see the super key and the candidate key. So this is very important because for calculating the closure key, why we are calculating the closure set means for identifying the what are the super keys and what are the candidate keys present in the given relation or a given functional dependencies. So super key is nothing but set of all attributes whose closure contain all attributes of the given relation. Candidate key is very much similar to super key. So your candidate key is nothing but the minimal set of attributes whose attribute closure is set of all attributes of the relation. For example, so in a relation, we can have the n number of super keys and also n number of a candidate key. So primary key, only one key is present inside the relation, but super key and the candidate key is n number of keys can be present in the particular relation. So if for example, a relation can contain A, B, C, D, and E, all the attributes can be present in the closure set means that can be called it as the super key. For example, my relation is A, B, C, D, and E, totally 5 attributes. My closure set, that is the A plus, if I calculating a plus, that is the attribute A closure I'm calculating means all this 5 attribute is present in the closure set means we can call it as a super key. So that is minimal set, that in that we have to check it in the left hand side part of the closure set. If it is a minimal set means that particular key can be called it as a candidate key. Now let us see the various example. Through that you can easily understand what is the closure set, how we can calculate the super key as well as the candidate key. So write down this example. Consider a relation, or is nothing but the table or a database, or we can call it as a relation. It can contain the 5 attributes A, B, C, D, and E, having the below mentioned functional dependencies. Here I am giving the 4 functional dependencies. One is A can determine the value of B, B can determine the value of C, C can determine the value of D, D can determine the value of E. So how we can calculate the closure set means, so for example, first I have calculated the A plus, that is the A is the attribute. So I'm going to calculate the A closure. First we're going to singleton attribute closure, we're going to identify. After that we can go for the 2, 3, 4 and 5. So in this case, I'm going to calculate the A closure. In my step 1, what are the elements present in the left-hand side? That we have to write it in the RHS. Here, A is the left-hand side element. That I'm going to add it over here. So, in the given functional dependencies, A can derive the, what is the next attribute? So, here we are checking A can derive the value of B. So, that value we're going to add it over here. Then we have to again check. So by using is there any B can derive the another value. So in functional dependency 2, B can derive the value of C. So that we're going to add it over here. Now we can check C. Is there any C can derive the value? Yes, C can derive the value of D. That we're going to add it in the closure set. Now we are checking D can derive any value. Yes, D can derive the value of E. So that we're going to write. So A closure can contain all the 5 attributes. If all the attributes is present in that particular closure set, we can call it as a super key. So this one is a super key. Now we can calculate the B closure. So B closure, B is through trivial inference rule, B can derive itself. So that only we are writing the B over here. So B can derive any value. Yes, B can derive the value C. C, we're going to write it here. C can derive any value. Yes, C can derive the value of D. That we're going to write it over here. So D can derive any, yes, D can derive the value of E. That we're going to write it over here. So B closure can contain the 4 attributes. Which one is missing over here? A. So this is not a super key. So why we can say this is not a super key means the definition of super key is it must contain the all the set of attributes in the given relation. So here the given relation is this one. It can contain 5 attributes, but here A is missing. So this is not a super key. Now let us see the C. Now calculate the C closure. C closure is whatever the element present in the C, the LHS, that we're going to write it as a RHS. So how we are writing this thing? By using a trivial inference rule, we can able to write the thing. So that we're going to write it over here. So by using S3, is there any any other attribute we can able to derive? Yes, by using a C, we can able to derive the value of D. So that we're going to add it over here. By using D, we can able to derive the value E. Now we can check whether this is a super key or not. So here all the attributes are present. No, A and B are missing. We can't able to derive. By using a C, we can't able to derive the attribute A and B. So this is not a super key. Similarly, we have to calculate the D closure and the E closure. So by using a singleton attribute, we have only one super key, that is a closure. So what is the definition of candidate key? How we can identify the candidate key? So candidate key is nothing but the minimal subset of the set of attributes in the closure set. So here minimal subset, here it is a minimal, A is the candidate key. So by using a, we can able to derive the we can say this is a candidate key. Similarly, we can able to calculate AD, AB, AC, AD, and AE. So through A, all the component, all the attributes related to A, definitely it will contain all the closure attributes. So now we have to calculate the candidate key, means it is a minimal subset. So no need to calculate all these things. So because this is only a minimal subset, because this is only a singleton attribute. So while coming over here, this is also candidate key as well as a super key, but here there is a two proper set. One is a, another one is a D. So this is not as per the candidate key rule, candidate key definition. This is not to be a candidate key. So A plus only the candidate key for this particular example. And also, how many super keys is present in this particular relation? How we can calculate this thing means we have to omit the first one, A, because already we have calculated the A plus. So through A and A only, all the attributes to be present. So remaining, how many attributes are there? 4 attributes. So 2 to the power of 4. So 2 to the power of 4 is nothing but the 16. So in this particular relation, there is a 16 minimal keys are present. That is a 2 to the power of 2 to the power of 4. So totally equal to 16 keys are present in the here, because 2 into 2 is 4, 4 into 4 is 16. So in this particular relation, there is a 16 super keys are present and only one candidate key, that is the A plus. So why we are not seeing this thing means here you are having a two subset, one is a another one is a D. So here you are having only one value, that is a only present it over here. So no need to go for a thing. So that is a thing over here. So I think everyone understand this one. If you are solving more problem related to that, you can able to easily understand the what is the how we can calculate the closure set and how we can calculate the super key as well as the candidate key. Now let us see the another example along with the table. So this is a second example. Consider the table student detail having, it can contain the 4 attributes. One is the roll number, name, marks, and location. So as the attributes and having only two functional dependencies, by using the thing, we have to calculate the closure set. One is the roll number. By using a roll number, we can able to identify name and mark. By using a name, we can able to identify the marks and location. So one thing is, keep in your mind, so before solving this problem, you have to know all the inference rule. That is the Armstrong axioms rules. Definitely by using that only, we can able to calculate the closure sets. So first we have to calculate the singleton attribute. So why we are using only a singleton attribute means that is a minimal subset. So here they are asking only the closure set as well as the candidate key and the super key. So we know that candidate key is those having the minimal subset, that we can call it as a candidate key. So only first we are checking with the singleton attribute. So here I'm going to calculate the roll number closure. For the roll number closure, first we have to do trivial attribute itself can be a derived. So we can write it the roll number. So by using a roll number, what is the another thing we can able to derive? Check it out in the functional dependency. Here by using a roll number, we can able to identify the identify the names and the marks. So we have to write names and marks. Now, by using a mark, is there any function? No. So we can't able to check. So the next thing is a name. By using a name, is there any attribute? Yes, here we are having a marks and location. So mark is already present. So you have to omit that one. Now add the location over here. So through that only, we can able to calculate the closure sets. So next we're going to see the name closure. So for the name closure, directly through trivial attribute, we can able to write because itself it can be derived by using a trivial dependence. So we can write the name. By using a name, what are the other attributes we can able to derive? That is the marks and the location. So that we're going to add it over here. So next, we have to calculate the mark plus and the location plus, similarly what we discussed in the previous thing. And also you can able to write down roll number and name, roll number and marks, marks and location. Through that, we're going to identify the remaining closure sets. So which one is a super key? This is a super key. Why we can call it this is a super key? Because here all the attributes are present in the given relation. Given relation, you are having a 4 attribute. All the attribute here, it will be a present. So we can call it as this one is a super key. So, and also whether checking this is a candidate key or not. So here in a right-hand side, left-hand side, it is only a single attribute. That is a roll numbers. That is a single set. So minimal subset only a candidate key. So this is also a candidate key. So in this particular relation, you are having only a single candidate key. So how many super keys are there? Here, leave the roll number. By using a roll number combination, all the thing to be a super key. So remaining, what are the element? 3. So 2 to the power of 3. So what is the value of 2 to the power of 3? 2 into 2 into 2 into 2. So 4. 4 into 2. So totally 8 super keys are present and only 1 candidate keys are present it over here. So similar way only we can able to solve all the thing. So this is the easiest way, and also by using a simple technique we can able to identify the closure sets of a given functional dependencies. So next also I'm going to show you one more example. That is the relation having a 5 attribute. I am giving the different functional dependencies. Through that, you can able to identify things. So similarly, here we are calculating the A closure, B closure, C closure, D closure, and E closure. So in this thing, none other attribute, no attribute can contain all the attributes present in the given. So in your singleton, you doesn't have any attribute, any super key or candidate key. Now we can go for the double hand. So now we're going for the double hand. After that only we can calculate. So and also doesn't have the anything means definitely nothing attribute can have the no attribute can having the super key and the candidate key in this particular relation. So these are the various example I quoted over here. Same thing I have uploaded in the courseware. Please go and watch this video as well as the courseware, because all the problem I already uploaded in the my courseware link. So in the description also I will give you the courseware link. Please go through that one. So these are the various assignment problem. So these are the major thing in your closure sets. So closure set is nothing but under the conclusion, the closure set is nothing but it must contain the set of attributes. So that is functionally derived from the given functional sets. That is a closure set of an attribute. It is denoted by the symbol F plus. And also by using this thing, we can able to identify super key and the candidate key. Super key is nothing but the set of attributes present in the given relation. Based on the given relation, all the attributes is present in the closure set means that is a super key. So based on the super key only, we are calculating the candidate key. Candidate is nothing but the minimal and proper subset that can be called it as a candidate key. Okay, if you have any doubt, please put the questions in the comment link. So definitely I will resolve your problems. Thank you.